Good afternoon, good evening, and good morning, everyone, depending on where you're connecting from. My name is Matteo Grassani. I will be your co-host for today's webinar, together with Marco Ferrarese. We have a stellar panel to discuss quantum computing in finance. That's not an easy topic, but it's very hot. You have heard probably just days ago, HSBC announcing to the world that they think they got some breakthrough in applying quantum computing to bond trading. And we will ask our experts whether that is really the case. Everything is where we are in terms of development, and especially from a financial investor perspective, is this the time to invest in quantum computing? Is it too early? Is it too late? We'll ask them. So let me introduce you quickly our panel, going alphabetically. We have Davide Corbelleto, who is quantum specialist at Banca Intesa, and he also has a past as a professor in physics. We have Federico Mattei, who is a quantum business development at IBM, and also has been a professor in physics. And we will join us a bit later also Steve Suarez, who is a senior consultant at McKinsey, CEO of Horizon X, and also has been guest lecturer at just join us, fantastic, at MIT. And you know that quantum computing started at MIT just after in early 80s. So without further ado, and sorry, cannot forget, we also have Professor Ioanid Rosu, our mentor for the HSC Finance Community, is the director of the International Masters in Finance at HSA Paris Executive Education. And he will have some questions as well for our panelists. So Marco, let's start our journey today. We'll stay 1 hour together. If you have any questions, please put them in the chat. Marco, you go for the first question to our panelists then.
Okay, sure. So Federico, we start with you, and let's start from the beginning. Okay, we want to build the basics. Okay, so the first question is about the fact that quantum computing is described as radically different. Okay, so at the most fundamental level, what makes a quantum machine different from a classical one? So basically, Federico, can you please sum up a century of physics in about 3 minutes?
Yeah,
just to start easy.
Thank you very much, Marco, and everybody for inviting me. So, what do we mean with radically different? We are using quantum mechanics, so the laws of physics, that rules how particles behave, also today in our computers, but we are using just some part of them. We know that leveraging on other laws of quantum mechanics, we expect to be able to reproduce some physical phenomena and some algorithms which we cannot solve with traditional computers, or let me say we can solve with some approximation. So we can line a parallel with the transportation world. So we can imagine at the beginning of last century, when all the transportation on Earth was done on the wheel. So we were using one simple principle of physics, let me say, to move transportation means around the world. But we understood that we need other kind of laws of physics in order to do long distance transportation. And for that, we leverage on different principles of physics, in particular on lift. And so at the beginning of the 90s, Brothers Wright started to build this prototype of airplanes, which are leveraging different kind of physical principle in order to transport peoples and stuff. And now we know that it's possible to transport people with different means, depending on the route, depending on the distance that we would like to cover. In computation, it will be very similar. We still today have some principles that we leverage on using our computers, our smartphone, all the supercomputers around the world. All of this stuff are leveraging simple principles of physics, the same. Now we introduce other kind of principle, superposition, entanglement, interference, to build different kind of computers which will help us to solve problems that we cannot solve today.
Okay, thank you very much. And Davide, we just heard from Federico how quantum computing is fundamentally different. Okay, but from the viewpoint of banking and financial services at an intuitive level for now, what does that actually mean? What kind of problems could quantum computers realistically help us tackle?
Okay, thank you, Marco. If I may, before answering your question, I just want to add a comment, because let me say that quantum computing is radically different, not only from a hardware perspective, as Federico said, but also from a software perspective, as well from the algorithmic design, which is used, of course, to implement the solution you are trying to figure out with quantum mechanics principles. So, although from the theoretical perspective, at least in its digital form, let me say, we are talking, quantum computing is a universal computation model. And especially when these quantum computers will be sufficiently stable and powerful to ensure service level agreements, we need to keep in mind that this type of computation will be used almost exclusively to solve specific type of problems, whose solution currently are obtained with classical computers are suboptimal, both in terms of execution speed or output quality. Or there's also the case of some type of problems which are intractable. So, turning back to your question, from a financial services point of view, realistically speaking, I see three potential areas where the application of quantum computing could be beneficial. First, optimization problems, such for example, the dynamic optimization of financial portfolios or treasury cash pooling system. Indeed, optimization can be reformulated. Let me say it better. Optimization problems can be reformulated as problem of finding the ground state of a quantum system. And this kind of reformulation can be properly simulated by another quantum system, for example, a quantum computer. Then another important use case are stochastic simulation, which are used essentially anywhere, for example, in a bank. You can use them to estimate risk indicators, calculate derivative pricing, generate a stress test scenario. And here, let me say, the quantum computer's ability to generate real random numbers, it's a game changer, because it means you are able to generate real random distribution, which is an essential point in order to improve the intrinsic convergence of the models. And then finally, of course, there is also machine learning. Speaking of supervised models, we know there are still there have been still studied several quantum alternatives to the best-in-class classification and regression models you can use. And these equivalent algorithms can ensure similar, if not in some case better, accuracy of the output than their classical counterparts, while using fewer data and, more important, fewer epochs. So significantly reducing the training time and therefore the related energy consumption, because we know that training a supervised model can be really, let me say, not environmental friendly these days. Furthermore, despite the hype which has been generated by LLMs in these last years, machine learning isn't just confined to neural networks and transformers, but also encompasses also unsupervised learning and reinforcement learning, which I think are two topics which of course are still being researched intensively also on the classical side, partly due to the fact that the results of classical models are suboptimal. And I think it is precisely these two are precisely the two areas which include, of course, techniques like clustering and genetic algorithms, in which I expect quantum computing to make the most significant difference in the future.
Good. And on this one, Steve, I see the first two panelists, of course, they touched on, setting the scene. It's a lot of technical jargon, but you have worked in banking and financial services for the last 30 years. And I'm sure you are still today, and you have been in front of investment committees, and it's all about capital allocation, risk-adjusted returns. So if you were to present today to an investment committee, a business proposition to invest in a quantum computing startup, how do you see it from an investor perspective? How would you frame the business opportunity?
Yeah, I think AI is actually helping us in this situation, because a lot of companies and a lot of people feel like they lost out on AI. It caught them by surprise. And so they don't want there's a lot of FOMO out there with this technology, and there's the fear of missing out. And so a lot of people are getting involved in quantum to really understand, how can they take advantage? How are they ahead of the game? And doing that. And so it's good for quantum. It's good because now it's getting a lot of exposure. On the other side, there's a lot of hype, and there's a lot of people that are, well, I have a quantum computer, or I want a quantum computer, and not they don't understand it as well as far as what it can do. And I think David was doing a great job trying to explain kind of where the value is. And so if you think about where quantum can beat classical computers, think simulation, think optimization, and then obviously you mentioned machine learning, but also in security, so quantum communications. It's not quantum computing, it's more quantum communication, so you think around security. And so I'm getting obviously approached by a lot of VCs, a lot of family offices that want to invest in this area because they're hearing a lot of money coming in. I don't know if you've seen the news, but companies like Quantinium just got $600 million with a $10 billion valuation. I was sitting on the board of Quare Computing, which is neutral atoms, that came out of MIT and Harvard. We got $250 million from SoftBank, Google, and NVIDIA just about 3 weeks ago. And there's a lot of money coming into this industry, which gives us a lot of the money needed to keep growing and driving through this. So from my perspective, I really advise people that aren't into quantum is to educate themselves, understand what this technology is, but more importantly, what it isn't. You're never going to get away from classical systems. And you're only going to use quantum very specific for very specific use case. So if you imagine sending a workload to different systems, most of the work will be done on classical systems, and very precise work will go out to the quantum computer, come back and work in more of a classical method. So trying to understand what it is. And that's why I saw a need in the market, and we created a course for executives at MIT to understand the technology at a high level. I'll tell you, when I was at HSBC and I was the head of innovation, we had 64 CEOs in different countries, right? We had 64 different countries. And I gave them training from MIT for free. The training was 6 weeks and it was about 4 or 5 hours per week. How many people do you think took advantage of that training? So just anybody on the phone, just guess what number you think said, Steve, I love it. Sign me up. I'll do this. And by the way, I did it for free. So I got MIT to give me this training, cost them $2,500. I did it for free. 3 CEOs. Actually, it was zero. Zero CEOs out of the 67 took advantage. Do you know why? They just didn't have the time to invest to go through this. So I deliberately went to MIT, created a course that within 6 weeks, so it's self-paced. You could do it as much as between 8 to 10 hours total. You can educate yourself on quantum, and so I am seeing a lot of people getting interested, but they're interested because they don't want to miss out like they did on AI. I hope that answers your question, Matteo.
Oh, it does, and maybe also spurs a follow-up question because again, you have a privileged position. You have been all over the world, Asia, the US. Now I think you're based in the Middle East, which is thriving on innovation in Dubai. So what kind of investors do you see, approaching quantum? Is it the family offices? Is it the institutional investors? Who is best placed, or is who are the first movers, let's say, in investing in quantum today?
Well, the pure play quantum computing companies are all privately held, right? And so when you think about that, that's more VCs and private equity that are coming in. You've got governments that obviously want to do so. I think these companies privately held, pre-profit, mostly R&D. They're early in their commercialization, and so think about seed, Series A type thing, and these VCs are typically people that want to specialize on deep tech, higher risk, right? Because you're talking about 7 to 15 year, very illiquid markets. So those are the kind of the investors that are jumping in today. Obviously, family offices want to get involved in different companies like that. Now, there are institutions that are getting involved, and there are institution investments that you could look at. So I'll give you some examples. IBM is working in superconducting. I know we got Federico on here. And one of the things that I published was some work that I started before I left HSBC, that we used a real quantum computer with real data to see if we can increase the probability that an investor would accept a bond trade based on the different pricing, and we proved that out, that we could increase that by a number. I think it was 36%, which is very significant. That day, and you could look at this. You could go look at when I published it on LinkedIn. That day, IBM's market cap went up by $13 billion, and HSBC's numbers went up by 10%. So, people are getting value out of it today, even though we're still in the trial phase. I'll just mention a couple companies and then we'll move on. But Google it also does superconducting. Amazon is doing, it's called Amazon Bracket. They bring different types of companies and you could use it on the cloud. So you could use trapped ions, you could use neutral atoms, the silicon spin and all this other stuff. Microsoft, they're doing topological qubits, but that's not ready yet. So they're doing other investments like atom computing and stuff like that. And then you have Honeywell, that is a big investor in a company called Quantinium. And that's that company that just got 600 million and a $10 billion valuation. They're doing a type of quantum computing called trapped ions, which are the different modalities that are there. So sorry, a bit long, Matteo, but...
Oh, I think excellent. Actually, I mean, the summary is deep tech, but it also requires deep pockets, especially because that time horizon. And so, but Marco, before we move on, maybe Ioanid, I know, and Ioanid Rosu is the director of the International Masters in Finance at HEC Paris. I know you're an MIT PhD. You have a lot of passion for quantum. Anything to add from your end, or any question for our panelist?
Yes, I actually I was at MIT studying it from '94 to 2004. So I had two PhDs, one in mathematics and one in finance. So I've seen. I unfortunately at the time I did not know how important quantum computing was, so I did not spend as much time. So I'm very happy to learn from the present panelists who have an amazing depth of understanding of these topics. But I do have a question which may sound a bit nerdy, but it's about how can we think of, because I learned classical, I was a computer scientist before I was even a mathematician, and I studied, I learned classical algorithms, which are kind of a sequence of instructions with 0, 1 bits and things like that. But then quantum computing algorithms, like what makes them different in your opinion? Is it some kind of superposition of states and qubits? I initially thought that quantum computing was some kind of parallel computing, which was another buzz term, but apparently no, it's more like a rotation things where you take a whole continuum of states all at once. Is that what makes them special? Perhaps that's a nerdy question, but that's what I would like to know if that's possible.
Maybe I'll try to answer to this question, and it also will bring us in an explanation of the basics of what quantum computation is. So I maybe cited some principles of quantum mechanics that we took from quantum mechanics to do quantum computation, and I think the first one, one of the most important one, is superposition, which is a property of particles, which even if they have a finite number of classical states, so took an electron, it can rotate in one direction or in the other, just two, but in reality, in nature, we found these electrons in a superposition of these classical states. So to try to understand this particular property, we can imagine a coin. A coin could be in just two possible positions, head or tail. But if we flip the coin on the table, it is not a head and it's not tail, and we cannot also say that it is both head and tail. It's just spinning on the table. It's another state. We can say that is 50% head and 50% tail. And if we would like to know which is the right measure, we have to put our hand on it. So if you apply this to bits can be 0 and 1 in the regular computation. But if we apply superposition to a bit, we arrive to have a quantum bit, which is the qubit. Quite famous are the information bringer of any quantum computer. And we can put this qubit in any kind of linear combination of 0 and 1, which is an infinite number of states. It can be represented as the surface of a sphere. Well, if we imagine that we can put all this bunch of information in just one single qubit, it started to tell us why it's very important for us to leverage on this principle. The other side of the problem is that if we would like to measure this qubit, it will give us just 1 or 0, exactly as the coin that will give us just head or tail. So we need problems, we need algorithms in which during the execution you need a large amount of possible state. So simulations, all the possible economic scenarios, or optimization, all the possible route between me and my destination. And then at the end of the algorithm, after having took in consideration all these possible states and scenarios, you have to converge to a solution or a subset of solutions. So this superposition enables us to analyze a very wide number of possibilities. And then if we are able to write a good algorithms, Davide was saying it's very important because also algorithms are changing. If we are able to write an algorithm which make converge all this bunch of information into our solution, we are good, we will be good quantum computing programmers. And the second property, I will be quicker here, is entanglement. Entanglement is a property which we cannot experience in our day life, and also it's very hard also for physicians to accept. Also, Albert Einstein have a lot of problems with entanglement. Entanglement means that two particles enter in a particular kind of relationship one to the other, and they are connected one to the other. So if we continue to imagine coins as particles, if we make two coins spin on the table, we can imagine that if they are entangled and I put my hand on one of the coin, the other coin immediately, even if it is on the other part of the city, it will fall with the same side of the coin I put my hands on. So if it's head here, it will be head also on the other side. It's something really counterintuitive for us. But in this way, you can propagate the information inside your algorithm with an unprecedented speed. And so if you couple this huge amount of information and this possibility to propagate your algorithm inside it with just this huge speed, you obtain a possible advantage that you can bring only to the problems in which you need all this information and all these connections.
Thanks a lot, Federico. By the way, I saw Steve Suarez was kind of nodding his head when I was asking the question, so I was wondering if he had to say something.
You know what? I'm a very simple person and I'm a business guy, so I'd like to bring things down to very simple concepts. The one that I use that seems to resonate is if you look at the difference between classical and quantum, and this is just an analogy, if you look at a very complicated maze, let's just say you had a maze, and you ask the classical computer to solve the right path to success, it would do it in a serial perspective. It would go down one path, come back, go down another path, and keep doing that until it finds the right solution. And then you could put more computers and try to do it in parallel, but it still kind of goes that. And going back to Federico's point, because quantum computing could be in multiple states at once, what it does is it goes through the whole maze all at once and it finds that optimal path immediately. And that's what makes it the exponential power of quantum computing. So it's amazing when it comes to looking at optimization, looking at simulation, and those type of things. So if you look at how it processes, because it's able to do it all in the same, it's multiple paths, it can go through the entire maze at once.
Amazing. Thanks.
It's an analogy. It's an analogy, but it
very useful. Thank you very much, Stephen, Federico, for the wonderful explanation. If I may ask one more question, which is related, since we're at the business school, I was wondering, because we know about the famous Shor algorithm of quantum computing, but I think that has more applications to cryptography. However, I heard there are other algorithms like HHL that solves like finds the inverse of a matrix much faster, and that is potentially very helpful in portfolio management in many other. Can you say perhaps something about how these quantum computing algorithms, what do they have in common when it comes to applications? And I assume they have many applications to finance, I would guess, but if you can say perhaps a bit more about that.
If I may jump in, Ioanid. So first of all, Shor's algorithm is not just intended to break cryptography, but you can also use some parts of that algorithm, which are quantum Fourier transform, to do other things. So you can use them, for example, to solve partial different equation and do other stuff. HHL is not just you can use it also to solve linear system equation. So it's something that is really useful in finance, and not only in finance. And so this kind of algorithm are let me say made up of some subroutines, which can be if properly combined together, can bring to other kind of algorithm which may solve other kind of problems. So the thing is that you have to be smart. It's like we were just hearing from Steven. So when you have a classical computer and you have to basically escape from a maze, you are in the maze. Okay, so you have to try to find a way to escape. But if you have a quantum computer, it's like you are out of the maze, so you can see the maze. It's not that is not ensuring you are going to find the best way to escape the maze, but you can see all the possibility altogether, because basically you are not inside the maze, but you are seeing from the sky. It's like you have this big picture, and also to, let me say, comment what Federico said before. Quantum computing is precisely the best paradigm you can use when you have problems which basically can accept more than one solution. So it's not good if you want to try to solve problems which are deterministic, so in which you have just one solution, okay? But if you have problems like, for example, that in which you can be satisfied, for example, in an optimization problem, you can be satisfied from finding a local minimum and not the best one. This is definitely the best computational paradigm you can use in order to address this kind of thing.
Thank you.
Okay.
And applications to finance. We're gonna discuss this later on, or I'm curious as a finance person, it's a natural question to
hold the question,
Yes,
Ioanid, because we have
there.
it as well. Yeah, Marco, you go
Yeah.
first, but we have also a question on crypto. Is going to break the crypto bank or not? But let's hold it. Marco, on to you.
Okay, we can move on. So nice, thanks all. That sets our stage, and we've heard why quantum matters, what it can do, and who is betting on it. Let's go a level deeper into how this actually works. Guess what, guys, we are running late, amazing. We were predicting this, but we have to try to go straight to the point now. So Federico, we start this second block with you. And could you walk us through the core components of a quantum computer, so qubits, error correction, algorithms, that financial professionals should understand to make sense of the current state of technology? What should a financial professional know about it?
Well, Marco, I think we already discussed about qubits, and I think it's really enough. Let's turn to error correction. So I think all of us, we expect from any kind of electronic device to answer our problems, our algorithms precisely without errors. But it wasn't so at the beginning. So we needed to impose error correction also to our traditional, let me say, standard computers. Quantum computers are still in that phase in which they have errors inside coming from different kind of sources. And so I think the most important effort that all of technology producers are doing today is to reduce and remove errors from algorithms. even if these errors are still in the results of our actual current quantum computers, there are error mitigation techniques which enable us to obtain results also from this noisy processor. And that's why, for example, HSBC, which Steve was mentioning before, obtained important business results also using noisy quantum computers. So it's important for us to know that the road to have a fault-tolerant quantum computer is quite long. We expect in IBM to have our first quantum computer in 2029, but we can also obtain important results from this noisy processor that we have today, applying error mitigation techniques. So it's very important. Then regarding the algorithms, they are already being cited. There are a lot of algorithms. I think the only thing I would like to add is that what we are looking for now is to have what is called quantum advantage. So the moment in which we can obtain results from quantum computers that cannot be obtained using a classical computer alone. So this kind of advantage will be obtained in different moments in the history, depending on the algorithms. So there will be some use cases in which we will have a quantum advantage, maybe next year, we don't know, and other cases in which we will have quantum advantage maybe in 10 years. And we hope that, for example, the Shor algorithms, which is behind the security, the quantum attacks, will be one of the latest to obtain this advantage. We hope so, because our cryptographic systems are not ready now. So I think these are the important things to know, the basics to know about technology, of course.
Okay, thanks, Federico. So Davide, we go back to you, and maybe we will go a bit deeper answering Ioanid's question here. So once we have those building blocks in mind, okay, how do they start translating into real use cases in finance? So things like risk modeling, we'll be talking about portfolio optimization, or even fraud detection, okay? So what might be quantum actually do differently here?
Okay, let me say, I would start saying perhaps I would add a fourth building block to the one you mentioned, which is software, as I also said at the very beginning, and that is because the implementation of this new algorithm also introduces something new to the field of programming, and we have to deal with it. However, to turn back to your question, we already know that there are some notable subroutines, as I was saying just before, that allow us to build quantum algorithms that can replicate classical counterparts more effectively and efficiently. For example, people from my competence center, the team I lead in Intesa San Paulo, have focused a lot in the recent years on what is called quantum amplitude estimation, which is basically an enriched version of the Grover algorithm that was originally conceived to do unstructured search. And this kind of algorithm, for example, which is, by the way, we can consider it an equivalent of Monte Carlo simulation in the classical world, is quadratically faster than the best known technique of Monte Carlo simulation, and has also a better can lead to more accurate output. And so you can basically use it in lots of use cases, and we also did it. There are lots of peer review papers from my team that you can find on different scientific journals, which have been published since 2022. And the use cases, for example, in which you can use a better Monte Carlo equivalent are, for example, credit risk analysis or option pricing. So this is just an example.
Steve, I think, yeah. No, thank you, Davide. And I have lots of questions, but I'll hold them. But maybe, Steve, again, if you wear your hat as an investment banker or a financial services professional. I mean, we go back to the investment committee, and how can we de-risk an investment in quantum computing? Because we heard from Davide and Federico that a lot of energy is required, and today the world is hungry for energy. We know AI data centers are eating up a lot of energy demand. So there's also a lot of competition for energy. How would an investor de-risk his bet on quantum computing? What the major cost would look like, and how to mitigate some of the risks, because it's very complex still, the whole scene.
Yeah, I mean, I think it's a good question. I think getting exposure to some of these companies, when I talk about quantum computing, I love using a lot of analogies, right? So I always use the analogy, it's like running a marathon. You don't show up the day of a marathon and just start running. You have to do a lot of things before. And so what I try to do is tell people that you have to first get access to some of these computers. It is a different way of engaging, coding, driving through some of this. I did a lot of this at HSBC, and it's a different mindset. It's not your typical classical model where you have to go and develop. And so if you think that you're going to wait, and by the way, waiting is not a strategy. So what I'm saying is put a strategy around this, understand how to approach this. This is very unlike AI. When AI came out, everybody had access to it and you could play around with it. Quantum, you'll have limited number of machines, you'll have limited number of people, and you'll have limited number of resources. And so I believe, and you were talking about quantum advantage earlier, I believe that the companies that are going to be ready, that once the market and a lot of these companies, the quality of the qubits go up, the gate fidelity, all of that goes up. The companies that are going to take advantage of them are the ones that are going to start getting ready now, educating themselves and doing it. I'm not saying go out and go buy one. I would never actually say to go buy one, but I say get exposure to it, train up, start training your teams. One of the things that I do at MIT is I talk about a concept called quantum vigilance and quantum visioning. In quantum vigilance is the outside market. You don't have control of this. It's how well the hardware providers, the software providers are getting better, error corrections getting better, the quality is getting better, following the roadmaps, and understand, look, at what point are my use cases going to be good, so that when you find that intersection, that's when you're going to find commercial value in quantum. You're not going to just wait till the outside market gets there. And so the companies that know how to plan that well and say, hey, once IBM, once Google, whoever it is gets to a certain threshold, my use cases are going to do well. So what I used to do at HSBC were things like value at risk. We did fraud anomaly, fraud detection type stuff. And obviously what's got a lot of people concerned is on the cyber stuff. So think about post-quantum cryptography. The US government has put out 2 executive orders saying that if you want to work with the US government or sell to the US government, you have to be PQC enabled by a certain date. And so now it's becoming regulation, and regulators are taking advantage. So how do I get companies to be interested in? Well, guess what? Your regulators are going to come and tell you, I want to see your plans. I want to see what you're doing. And that's kind of how I get them interested. But at the same time, that's kind of the threat side. At the same time, I said, hey, you could take this as an advantage and look at it at the different opportunities on how you could implement it at your organization. And I don't make it just on financial services, but financial services are kind of between that and pharmaceuticals, I see are leading the way in this.
Okay, so basically, do not ignore and try to get in early, understand, and then there is a kind of faith that the use case will come. It's just a matter of time to unlock probably the right
There's a lot of
balance
use
between.
cases out there, right? And so I have a company called the Quantum Index, and where I index who are the top leaders by industry. So I've got automotive, I got financial services, I've got life sciences, and in about 3 weeks, I'm going to launch energy. And so I base that on, research papers and how their research papers are getting cited, the size of teams, the POCs they're running, how many patents those organizations have. So I take a bunch of different numbers to help calculate where we say who are the leaders in this. So sorry, Matteo, I don't want to dominate the conversation, but I just...
No, it's actually very interesting. A lot of follow-up questions. And I mean, Marco, maybe just one in a second. I know we're late, but it's also good. The conversation is flowing nicely. You guys are exceptional. And do you see, I mean, of course, the financial industry, it's very much adjacent to quantum computing applications. In your index tracker, and do you see any other industry which is or could become very much a use case for quantum computing beyond financial services?
I'm sorry, was that for me or for Marco?
No, for you. I mean, because you mentioned that you have a tracker, so that you're already tracking the industry. So I was just checking whether.
You know what? I'm going to energy. I think energy is going to be really exciting once we kind of launch that. Probably material science will be next. There's aerospace and aviation. I know Boeing and Airbus are doing and looking at this a lot. So listen, the reason I fell in love with this technology is that the applications are endless. It just depends on human creativity and how you apply it. The world around us is quantum mechanical, and so we know it's real. We just got to find smart people that can make it stable and see how we can harness that technology.
Excellent. Fantastic. Marco, on to you then.
Okay, thanks, Matteo. So we have been unpacking the machinery. Okay, we've been seeing how those pieces start connecting to the real world of finance and capital. Now, we want to see what's happening on the frontiers of research and investment. So what is happening right now? So with Federico, okay, people often talk about the two sides of the quantum moon. So the bright side with breakthrough computing power, and on the other side, the dark one with the potential to break encryption and disrupt security. So could you please help us in defining those two possible futures? Maybe we've been concentrating much more on the brilliant one, the bright one. And so let's introduce us into the dark one as well.
Well, thanks, Marco. Well, it's the same side. So we have a new kind of computer which is able to solve problems which at the moment are intractable for the current computers. Inside these problems, there are many of them which we'll be very happy to solve, and some of them have been cited by Davide, by Steve, and so we will be very happy to have this power, this computing power to solve these problems. Inside these intractable problems, there are also problems which we are today very happy to be not able to solve them. And these problems are the ones that we use to do cryptography, for example. So these problems are so hard that we trust that if we hide a password inside them, if we encrypt a password with this kind of mechanism, we are sure that nobody can obtain back my password or my safe connection from the larger number. Unfortunately, we know since 1994 that there is an algorithm we already cited today, which is Shor's algorithm, which enables us to solve the problems behind asymmetric cryptography using a quantum computer. Asymmetric cryptography is used for authentication to systems, so also for authentication to bank portals, for example. It's used for digital signatures, so contracts, certification, and it's used also to encrypt data at rest, data which are transmitted and something like this. So when we will have an enough powerful quantum computer to run the Shor algorithm, all this kind of mechanism will be possibly hacked. So the first thing to do is to identify new problems which are hard to be solved also for quantum computers. And this part is already been done. NIST, so National Institute for Standard Technology in US, but also equivalent institutes in Asia, already did certifications and standardization of this kind of problems. So today we already have some post-quantum cryptographic methods, and NIST is still today continuing looking for new cryptographic methods. So we have them. The great issue here is that all the institutions, not just the financial institution, do not have any kind of visibility on the cryptographic methods that they are using today. So if I say to an institution, so you have to change all your cryptographic methods, RSA 2048, and turn back them to this other one kind of cryptographic methods, they are not even able to start because they do not know where they use RSA 2048. So the most important thing to do today, and that's why it's important to start today this quantum safe journey, is that we have to do a project to identify where I use today cryptographic methods, and then I have to migrate my cryptographic methods to the new one. And also this stuff is very difficult because cryptographic methods are inside hardware. So I have to go to my hardware provider and ask them to have a quantum safe version of the hardware. It's inside software. Software is provided by third-party providers, and I have to go to them. But it's also developed inside my my company, and also developed by consultancies. And encryption is also inside digital signatures, connections, safe connections, and all this stuff. I have to span all of them and do an inventory, and then migrate all of this stuff. So even if as I already said, the Shor algorithm will reach the advantage, we don't know, in 5 years, 10 years, we don't know. We have to do all this migration stuff before the arrival of the advantage on the Shor algorithm. And it has been estimated that for large institutions, all this migration journey will take more than 10 years. So even today, we are late. Steve already cited the US. There are a lot of executive orders about the migration to post-quantum cryptography, but also in Europe, in UK, and a lot of other countries, we have post-quantum cryptographic roadmap which have to be executed. And the dates are, I think, quite all the same or in every country. So we have to migrate all the high-risk systems in 2030. And we have to migrate all the systems, also the low-risk one, in 2035. It's a very difficult challenge, not from the quantum point of view, but from the cryptographic management point of view.
Super. Thanks, Federico. We move to Davide. We are getting close to the end. So Davide, we need a flash answer on your end. So you are working hands-on to tangibly explore the potential of the bright side of quantum computing. So can you tell us now which results can you measure today with a quantum computer and what might be possible in the future? So what is hype and what is real?
Okay, so our center of expertise, our competence center, was founded precisely with the idea of exploring the potential advantages of quantum computing, especially since the threats posed are well known, as Federico also pointed out. Regarding results, the idea is to use always a progressive methodology that doesn't fuel false expectations, but helps to set them correctly, especially towards top management. And perhaps if I may have just a minute, it's worth mentioning all the possible approach you may use in order to solve a problem with quantum computing. Obviously, the best approach would be to use a quantum computer end-to-end in order to solve a specific task. And in this case, we are talking about full quantum algorithms. These algorithms are certainly the most promising because in some cases they can even offer an exponential advantage over the classical counterparts. However, they require coherent and scalable quantum computer to be executed. So probably these are the ones we will most get advantage from in the future, in 5-10 years. However, this shouldn't discourage you from conducting industrial research today, because even if the algorithm isn't ready to be executed, you will have it ready when it becomes possible to execute that. So this still offers a competitive advantage over competitors. Then there is a second category of algorithm called hybrid or variational, which involve the joint use of quantum computer and traditional supercomputing system. A typical example of this category of algorithm are supervised quantum machine learning algorithms I've already mentioned before, where maybe you want just to do the training part on a quantum computer. The advantage of this approach is that, of course, by being able to identify a precise point in the whole process where you really need to use quantum computing, if it's possible to execute that subroutine offline, and in such case you can even it's not a big matter if you don't have service level agreement by now, because of the computer scarcity also Steve mentioned before, and therefore you can let me say you can despite the hardware limitation, you can also bring partially in production this kind of workload. Obviously, the number of problems of this type is much more limited compared to the full quantum approach. So you need basically to be lucky and find a use case that fits this kind of problem. And finally, there is also an even more limited class of problem called quantum-inspired algorithm. Although originally intended to run on a quantum computer, if you are able to accept some limitation, certain restriction, such as, for example, in terms of speed up and accuracy, you can sometimes reduce to a classical form the originally quantum algorithm conceived in order to be run on specific high-performance computing architectures, which are classical. And while, of course, it's very difficult to find use case where this quantum-inspired approach can be effectively used, and also you have also to prove that these alternatives are more effective than the best-in-class classical algorithms. Sometimes it can happen, As for example, in the use case, our first quantum inspired use case we released in February in production, which regards the ATM cash flow optimization.
Yeah. And also, let me remind the audience that, Davide, you work for a bank. And so it really sends a signal back to what also Steve was saying, that investors and financial institutions are preparing for the quantum computing, which seems to be still a race, but we're getting there. We are really much almost at the top of our hour together. Maybe Ioanid, you are the director of the International Masters in Finance at HSE Executive Education. You also run a course on machine learning. I'm sure your students have a lot of questions on quantum. Any question from you to our panelists or comment?
Absolutely. First of all, thanks for this wonderful panel and this great discussion. And I'm sure our students will like to ask the panelists very quickly, what kind of skills should they learn in 5-10 years? What role should quantum computing play in the curriculum? What do you envision? Like what type of, when you will hire the next generation of HEC students, what do you expect them to know?
A lot of linear algebra.
HHL or just linear algebra?
No, I was joking, but I'm also serious. Let me say, you don't need to be a quantum physicist in order to do quantum computing. So the mathematics behind the required mathematics behind is basically lots of linear algebra, some analysis, sometimes some geometry. If you have particular problems that can be, for example, represented with a graph or this kind of stuff.
Remember that we are a business school, Davide. However, our math skills are not really improving that much, but yes, we should definitely keep. Yes.
It would be good to know also from Steve and Federico on the same question. What would you suggest? Because as a layman, I would say, well, maybe GPT in 5 years will do some of that linear algebra, but it's provocative. What do you think, Federico and Steve? Federico first and then Steve to close.
Yeah, well, it really depends in which part of the layer of quantum computation you will work on, because of course, if you would like to work on the hardware, you have to study physics, you have to study engineering, and that's it. Then there are different layers in the programming part. If you would like to develop from the core, it's very important, as Davide said, that you understood the basic mechanism, and at the basis there is linear algebra. Then on top of this, there are, let me call them data scientists that will leverage on the libraries of quantum computation to do their job. So regarding them, they for sure have to know very well their application domain, and then they can start to study this abstraction layer. So they really do not know to know everything about quantum mechanics. So from my point of view, it's very important to understand quantum computation in all its stack and try to understand where you would like to stay. Let me spend just one last word about the management part, because we already speak about a lot about technical challenges, but today it's very challenging for a manager to decide to invest or not in quantum. Because as Steve was saying, it's very different from artificial intelligence. Artificial intelligence, you took your artificial intelligence and then try to do some use case and you understood what's going on. Quantum mechanics is different from the basic. You are changing the hardware, you are not changing the algorithm. And so it's very difficult for decision makers to invest or not, to put people or not, and something like this on quantum computation. So also from the managerial science point of view, we have to do a lot of research to give them the managerial tools to manage this new wave of innovation?
That's a very good point, and thank you for that. I think, and Steve, last word to you before we come to a close. How you see it, because you're closer to the investors and the bankers, and they go hard on cash flows and models. So,
as a former business student myself, and just focusing from the business perspective, I think it's important to understand the technology and what it can do, and then take your problems today and see how your problems can get solved on this. So you don't need to understand the technology, because we have amazing physicists. We have people that really understand it. And I think it's partnering up business people that have business problems with the technology people that know how to solve those problems. And the combination of building those teams together is where the magic's going to happen. I mean, I could tell you a lot of problems. A lot of people don't even know how classical computers work, but we know you can use classical computers to solve those problems. So as a business student, understand your problem, understand what quantum there is advantage and where that advantage can be, and then apply those problems with people on the technical side, work together to solve it. I think there's a lot of amazing things. I think there's a role for everybody in quantum. It's just a different perspective.
Thank you very much, Stephen. And I guess the summary is that the rules of investing and investment never change. So it will always be a matter of dialogue between the investors and the technical folks. Thank you very much to yourself, Steve, Federico, Davide, Ioanid. It's been an extraordinary journey, just an hour together, but I hope that our audience got something out of this time together. Marco, thank you as well for co-hosting. I don't know if you have any last word. If not, I think we can come to a close and really thank everybody.
Just thank you all for being there, and to our panelists for making the quantum world a little clearer. And we'll share with you the videos later. And thanks again.
Yeah, we'll put it on our LinkedIn page. We'll put it on our YouTube channel. And of course, as Steve said, the magic will happen. Thank you very much, everybody, and have a good continuation of the day.
Thank you.
Thank
Bye.
you to all. Thank you very much.
Thank you.